Namaste everyone. Welcome to second PUC physics class. We were discussing about AC circuits, and in the AC circuits, especially electrical resonance. Namaste, welcome to the class. So we were discussing about electrical resonance, the series resonance circuit. We will recap the things and we will study a few more things about resonance circuit. And we were discussing about its application in the last class. So we have a resistor, inductor and capacitor connected in series across an AC source. An inductor like this connected in series across an AC source of alternating EMF. V is equal to Vm sin omega t, right? That was what we have considered equation 1. So this is R. And finally we came to know that in this circuit, the current may be leading or voltage may be leading depending on the reactance or depending on the frequency of AC. Frequency of AC is given by omega, and it is also equal to 2 pi nu. According to the frequency, inductor will give a reactance of 2 pi nu or 2 pi nu L, that is equal to omega L. And capacitor will give a reactance of Xc is equal to 1 by omega naught C, that is equal to 1 by 2 pi nu naught, 1 by omega C, any frequency may not be at resonance frequency only, 1 by 2 pi nu C, right? So at low frequencies, capacitive reactance will be highest and the current will be minimum. At high frequencies, inductive reactance will be more and current will be minimum. At some intermediate frequency, which is neither very high nor very low, there is a frequency called resonance frequency, at which inductive and capacitive reactances will match each other. And if you want to draw what is the phasor diagram, you know that voltage and current are in phase. Of course, if you have pen and paper, not if you have pen and paper, you must have a pen and paper, keep on writing it so that it becomes very familiar to you. So you must keep on writing this every time, then you can write it properly in the exam. So very important chapter, and understanding this one is very important, not only for theory exam, for also solving the problems, because problems become very easy once you understand all the theory. So voltage across the resistor is in phase with the current. Current through all the three components are same, there is no difference in the current, whereas voltage across the resistor is in phase with the current, and voltage across inductor will be leading and voltage across capacitor will be lagging. So here we show it like this, and this is the situation actually at frequencies which is low, right, lesser than the resonant frequency. And so you can subtract these two, right? So you will get Vc minus VL, and if you try to find out the resultant voltage between Vc minus VL and VR, finally remaining is this one and this one, then you will get a resultant like this. So this is the phase difference between current and voltage, and in this condition the current leads. Current leads the voltage by some angle phi, and that phi is given by tan phi is equal to, and you can write it, it's actually equal to opposite side. And what is this one? And if you want to write the peak values, it is VCM minus VLM, not VRM, VCM minus VLM, and this is VRM, this is VRM, this length, it is VRM, and this is final voltage V, right, Vm. So tan phi is equal to opposite side by adjacent side, Xc minus XL by R. And if you want to find out the full output voltage, that means whatever is given by the supply, full voltage across RL and C, then this voltage is given by V is equal to square root of VR square, voltage across R whole square, plus VL minus Vc whole square. In this it is VL minus Vc whole square, right? At low frequencies, I have written this wrong. This is VL. Voltage across the inductor leads, voltage across the capacitor lags. Voltage across the capacitor lags, current leads, and voltage across inductor leads the current. Okay, Vc minus VL. So Vc minus VL, Vc minus VL whole square. This is what we write. So square root of VR squared plus Vc minus VL whole square. So similarly we get the expression for Z, the total impedance, root of, so we put it as Im into R squared, Im into Xc, Im into XL, then Z is equal to root of R square plus Xc minus XL whole square. Hope you are following all these things, because already we have derived this. And you know VL is equal to VLM, voltage across L maximum, Im into XL, VCM is Im into Xc, VRM, voltage across R maximum, Im into R. R does not have any relation with frequency. R is independent of frequency. Resistance of a resistor, it doesn't depend on the frequency of AC, it doesn't depend on any criteria of the source. It is independent of all the criteria of the source. Resistance of a material depends only on its dimensions, length, breadth, length, area of cross section, etc. Okay, Z equal to root of R square plus Xc minus XL whole square. So tan phi we have written. Now cos phi. This is called power factor. You know that power in AC circuit is given by Vrms into Irms into cos phi. We have written this. We are going to derive this. All the derivations which are not so important for the examination point of view, theory examination point of view, I will do it at the end. Now for the time being I will narrate all the derivations, all the important points, then we will go to the derivation. So cos phi, if you want to write cos phi is adjacent side by hypotenuse. Adjacent side by hypotenuse. Adjacent side is Vrm by V, Vrm by V, and this is Im into R, Im into Z, because Z is this one, which is Vm by Im. Okay, this is R by Z. Cos phi is R by Z. So shall I write it only once here? Cos phi is equal to R by Z. Okay. So now in this condition the current is leading. If the frequency is very high, then XL will be more, and voltage across inductor will be more, and this will be longer than this one, so you'll have to go for VL minus VC. Now this resultant voltage will shift here for a parallelogram here, right? Then the voltage leads. So for all the frequencies above resonant frequency, voltage leads, and for all the frequencies below the resonant frequency, current leads. It is partly capacitive. Above the resonant frequency, it is partly inductive. At resonance frequency, it is purely resistive. At resonance, the circuit is purely resistive. Z is equal to R, right? Second one, I is maximum. So maximum current is maximum. Im is maximum. The peak value of current will be highest at that moment. The highest peak value of current will flow, and that is equal to Vm by R, because Z equal to R. Then, okay, third point, Im maximum equal to Vm by R. So that resonant frequency is given by XL is equal to XC. The inductive and capacitive reactances will be equal, and voltages across L and C will be equal. VL is equal to VC, and then what else? Yeah, Z equal to R. What else you get in at resonance? And power factor cos phi is equal to 1, because the phase difference between current and voltage is 0. Circuit becomes purely resistive. At that moment, current and voltages are in phase. This is at resonant frequency, and resonant frequency is given by 1 by root LC, right? Omega naught is 1 by root LC, and nu naught is equal to 1 by 2 pi root LC, because 2 pi nu naught is 1 by root LC. See how many formulas you have. Plenty of formulas in a single concept. When you start from purely resistive, purely inductive, and purely capacitive circuit, when you combine all together, starting from that purely resistive up to this resonance circuit, everything is common, so you are clubbing everything together. So now this is the final conclusion that we have got. Now how do you show this phase difference between current and voltage at this instant? Of course, we have studied this circuit at the time of frequency which is lesser than the resonant frequency. At this condition we are analyzing it. So, but these formulas hold good even for the frequency greater than the resonant frequency, because you see here it will be VL minus VC, but when you square it, it will not, never be the different formula, it will be the same formula. Okay, now what else I want? I want to put the waveforms and the phasor diagram like this. Yeah, waveform and phasor diagram. Yeah, if this is the voltage, hope you can see this completely, right? If this is the voltage, you can see this one here. Yeah, if this is the voltage, V is equal to Vm sin omega t, how will be the current? Current leads. Leads means it will be, and it is not leading by exact 90 degree. It will be leading by some angle which can be given by either tan phi or cos phi, any one. Cos phi is formed here, right? So you have to start from somewhere here, this one. Its peak value will be somewhere here, and it will be following this one. Okay, right, you have to shift it a little bit, right? Yeah, I will draw this again. So a little, you have to follow little rules here. You can't draw it as if you want. So it will be increasing, and by the time it decreases, so here, yeah, right, like this. Okay, I can draw this now. So it will be like this, and it will be always having a phase difference like this. See here, when it increases, when this is 0, it has already increased, but it is not 90 degrees, so you have to start a little bit later. So like this, so it goes here. Hope you can see this, right? You can see this one. Okay, let it be now. So this is I and this is V. V equal to Vm sin omega t, but I is equal to Im sin omega t plus phi at that condition. This is the phase difference from here up to here. This is the phase difference between current and voltage, phi. And how do you show this now? So you drop a line here corresponding to some angle omega t1. Shall I use the same line here? Okay, like this. Omega t1 at certain condition. Current will be leading, so you have to get the equation for current somewhere else. Okay, I can include cos phi is equal to R by Z formula here, right? Yeah, so current will be somewhere here, and voltage will be somewhere here, right? This is the voltage phasor, and here is the voltage phasor, this one V. And what about current? Current will be somewhere here. But now this time this angle is not it is not 90 degrees. This angle is phi. It is phi, and this height should be shown in different ways. This is Im. Okay, I will show this one. This is Vm sin omega t, right? This is Vm sin omega t because this corresponds to voltage. Vm sin omega t. What about this one? This one, Im sin omega t plus phi. Correct? So this is how do you show the way in which you show the phase difference between current and voltage. It is phi. Now it is current is leading. So at resonance, both current and voltages will be in phase. Circuit becomes purely resistive, and power factor becomes 1. Phase difference becomes 90. So you know the difference between cos phi and phi. Phi is the phase difference, cos phi is the power factor. So this is called power factor, but phi is only phase difference. Okay, now we will go to that important factor. You know that when a resistor, inductor and capacitor are connected in series across an AC, what you call resonance circuit, it picks up only one frequency. What do you mean by that? It selects one frequency. What is the meaning? It allows the current to flow through in the circuit for only one frequency of input AC. You set the input to a peak value of 10 ampere to minus 10 ampere. Whatever it is, either it is 100 ampere to minus 100 amperes, current in the circuit is 0. Why? Because you have not set the frequency to a suitable value. That series resonance circuit has its own natural frequency. If you set the input frequency or the frequency of that AC to that particular resonance frequency, which is given by this equation, then only the current flows in the circuit and the current will be maximum. If you set a frequency, number of cycles repeated per second, just below the resonance frequency, current decreases. That is because of the trouble given by capacitor. It gives highest reactance. If you set the frequency just more than the resonance frequency, again the current drops. It will not be highest value. So if you draw a graph of current versus the frequencies, then you get a graph like this. You know it, right? Shall I, can I rub some of the formulas? I think, no. Everything is needed now. So if I draw a graph of resonant frequency, frequency versus current, at one particular instant, the alternating current will have its highest peak value. In other frequencies, at lower frequencies, of course it is alternating current, its peak value will be less. And at higher frequencies, again its peak value will be less. Hope you can follow this. At resonant frequency, its peak value is highest. That's why this is one of the peak value which is highest in value. So I am maximum. Because every time we get alternating current, whether it is lesser than resonant frequency, whether it is resonance frequency, whether it is more than resonant frequency, we are getting alternating current which will have its numerous instantaneous values. Among them, one is peak value, and that peak value will be highest at resonance. That is why it is called IM maximum. And this is the way in which current varies with the frequency. So here in x-axis we have frequency, and I call this as resonant frequency, and this is lesser than resonant frequency, this is greater than resonance frequency. Say the resonant frequency is 500 Hz. That example I was discussing in the last class. Now we came to the point where we were discussing in the last class. This is frequency here on either sides, and say this is omega naught, this value, say it is 500 Hz. So if you set the number of cycles repeated per second in this circuit for 100 Hz, 200 Hz, current will be less, and here XC is greater than XL, much greater than XL actually. What about here? XL is much greater than XC, so they won't allow the current to flow through. But at resonance we get Z as the minimum value, and XC minus XL will be 0, because X equal to XL, you get the highest current. That means that circuit allows only one particular frequency to flow through it. I think you can understand this sentence now. A resonance frequency picks up one frequency. What do you mean by that? If you supply an AC which has a particular frequency, then that circuit will give the current only for that AC which has got that particular frequency. If you feed that circuit, resonance circuit, with an AC source which is set to some other frequencies than the resonance frequency, no current will flow through the circuit. So that is why it is also called selector circuit. Resonance circuit is also called, series resonance circuit is also called selector circuit. It selects the resonance frequency and rejects the other frequencies. It selects the resonance frequency means it gives very good current to flow through in the circuit. It allows the current to flow through in the circuit only at resonance. It doesn't allow the current to flow through at frequencies other than the resonance frequencies. Okay, now we will come to the important part of this. Wow, how do you apply this in the, so that is what we were discussing. What is the application? That is that is what we call, one of the application we were discussing about was radio, right? In radio communication, a radio will always have a circuit, resonance circuit, right? Shall I rub it here? I think from the timing, this is not needed, right? Okay, now this is not needed. Okay, I'll rub this. So any radio will contain this resonance circuit. Radio will contain, so this is the inside radio, right? Radio will contain this. What is this? This is actually fed from the antenna. So antenna will feed this. Antenna will receive all the signals from different radio stations. Suppose you open a radio station, then government will give permission to send the signals only in a particular frequency. That is what is called the radio wave frequency. So for example, people say when they announce, the radio jockeys, when they announce the program, they say it is Red FM 93.8, 98.3 FM Radio Mirchi. They say like that. So that 98.3 is megahertz. It is the frequency. And all the programs, what they do in their radio station, they must convert it into electrical signals, recorded program, and that is in electrical form, and that electrical signal has to be converted into electromagnetic wave, and that electromagnetic wave must have a frequency of 98.3 megahertz, or whatever the frequency permission is given by the government to you. Every radio station will have its own resonant frequency power permission given, and they will send all their program signals in the form of electromagnetic waves, and the frequency of that electromagnetic wave will be that frequency, which is the given permission, and that electromagnetic wave will travel. And radio, the signals from Bangalore station, signals from Mysore station, Madikeri station, Bangalore station, Mangalore station, all the signals will come and they will be received by the antenna. Antenna will feed it to the series resonance circuit inside, and all the signals will try to enter into the series resonance circuit. But if that series resonance circuit, if its resonant frequency omega naught is equal to 1 by root LC, or nu naught is equal to 1 by 2 pi root LC, if it matches, if these values of L and C are such that the answer that you get, the resonant frequency, exactly matches with the signal frequency of that radio station which is entering into this when it is received. If that frequency and the resonance frequency or the natural frequency of that RLC circuit, series resonance circuit, if they match each other, then that signal can pass through the circuit. What do you mean by that signal can pass through the circuit? Now the circuit gives a fairly good current only for that frequency. What about other frequency? They are rejected. Let me give some examples for this. I'll rub this. If needed, I will remind the formulas. Oh, this is needed. This is very much needed. Okay. XC much greater than XL. Yeah, here frequency. This is omega naught S. Now, so suppose radio station A, radio station B, C, D, and all these frequencies are in megahertz, but I will take the example of 500 hertz. Say, suppose the resonant frequency of this is 500 hertz. Resonance frequency of this, when I substitute L, C values and I'll calculate this, I say I get 500 hertz. Suppose the radio station B is sending signals at 500 hertz. Government has given permission to radio station B for sending signals here, and radio station A is sending signals in 700 hertz. This is in 1000 hertz. Say this is in 2000 hertz. What happens now? All the signals will enter into the radio through the antenna. Antenna will feed it to the series resonance circuit, but you get a current only for one frequency. What is that? This one. That means those radio station signals are received by the circuit. They are converted into electrical signals and they will be heard. So you can hear only that particular signal. What about the other signals? They can't pass, they don't give enough amount of current, so you don't receive it. So what do you mean by not receiving? That means no current will flow through that circuit for those signals. Sir, I want to hear station A. What I have to do? I have to change the resonant frequency of that circuit. So if I want to change the resonant frequency of that circuit, you have to set a RLC circuit inside that radio, which will give you, when I substitute L and C, the answer which is exactly equal to 700 hertz. But it is not giving 700 hertz now, it is giving 500 hertz. So what to do? Change either L or C. That is what you are changing in the radio. When you change, so you might have seen old radios where we turn a knob, right? When you turn the knob, we get, we can hear different radio station. How is it possible, sir? When I turn a knob in the radio, nowadays digital radios have some digital signals and you can change their values immediately. But in the olden radios, we had one turning knob. When we turn that, there was inside a capacitor. You know that capacitance of a capacitor depends on the distance between the plates and the area of the plates, right? Epsilon naught A by D. Now this distance is varied. When you turn the knob, you are actually changing the distance between the two plates using a screw. So when the distance between the plates is changed, capacitance of the capacitor will change. When the C changes, total nu naught changes. When you change it in such a way that when this answer comes to be 700 Hz after changing the capacitor, now this signal can pass through the circuit. 500 Hz is rejected because its whole resonant frequency and all the graph will be shifted here. Now the maximum current flows through the circuit for 700 Hz, not for 500 Hz. Hope you have followed this. So for 700 Hz, now the circuit gives good current because it is its resonance frequency now. You can hear station A. Now you can't see here B, C, D. No. So by changing the capacitance value, by changing the distance between the plates of the capacitor, we used to change the resonant frequency and thereby hearing different radio stations. So remember, if a radio is switched on, it receives all the signals from all the radio stations, but only one is picked up in that. Which is picked up? It is the one whose the signal frequency is the natural frequency, resonance frequency of the circuit. And if you want to receive other stations, you have to change the resonance frequency by changing the C value. Every time you can't remove a circuit and put another new circuit into that. That is not possible. So you have to go on changing the capacitance only. That is one thing. Okay. So even TV communication also requires the same type of resonance. Because in TV communication you will send a lot amount of signals. Of course, TV communication signals are very complicated than radio communication signals, because in radio communication you need to send only audio signal. What about in TV communication? You need to send video as well as audio, and you should have many other signals along with them, because if one video is sent to the from the transmitting station to the receiving station, along with that you have to send the audio. And you have to give another signal which says this is the particular audio of this video, because there should be a synchronizing signal. Otherwise, when the serial is going on, the video will be of serial and audio will be of news, and it will not be very fair to see, right? Such things, or it may be very comedy to see sometimes. If audio is of news and video is of serial, then they won't match each other. So there should be a synchronizing signal, and even in the video you have to send different signals which represent all the brightness, contrast, and so many things involved in colors. All these signals have to be sent together in order to recapture the same picture that was in the transmitting station. So that needs a lot of these signals. So usually when the government gives a permission for a radio station, it gives one frequency. Not exactly one, but still theoretically we can take off one frequency. In one frequency you can send sound waves. Of course there are some signals needed along with that. That is the frequency of transmission of that radio station, in the frequency of radio waves that it transmits. But whereas when you open a TV receiving station or transmitting station, if you are opening a TV channel and if you want to send some programs into the TV receivers, then you should get a permission from the government, and government will not give you a single frequency. It will give you a range of frequencies. What do you mean by range of frequencies? So much megahertz or some amount of hertz to this much. Say 700 hertz to 1000 hertz. Why is that? Actually it is not 700 hertz to 1000 hertz. It will be a long range. Say why it is a range? Because if you want to send signals corresponding to a picture and its audio and its synchronizing signal and all the picture informations like color brightness, color hue, color contrast, everything, you need a lot of signals. It is not possible with a single frequency. You need a band of frequencies. That is what you call band. Now we will come to the topic. You need a band of frequency for communication. So even in TV, even in radio communication, even in mobile communication, resonance theory is needed. It's the basics of all these communications. You see, this mobile is also a selector, isn't it? When you are holding your mobile, you are standing at a point where there are enough amount of signals. You are receiving the signals from all the mobiles in this world. Most of the mobiles, but your mobile receives only one signal. That is the resonance frequency of that mobile, RLC circuit inside the mobile. Imagine how will be the situation if there is no resonance. Suppose this is your mobile, right? This is you. Okay, say you are A and your friend is B, your friend is C and your friend is D, right? Okay, your friend D calls X and your friend C calls Y, your friend B calls U, right? Or say friend C calls U and friend B calls Z. All of them are having mobile. Hope you can understand this explanation, right? So like this box explanation. You are A, it is you, and your friend D calls X through his mobile. He presses the mobile number of the friend X and he calls him. Friend C calls you. That is your number, your mobile number. He presses your mobile number in his mobile C and presses call. What about friend B? He is calling somebody else, Z. Now what happens? Whether the signal sent from D goes only to mobile X? No, it goes to all the mobiles. It goes to mobile X, it goes to mobile C, it goes to your mobile, it goes to Z mobile, everywhere. But your friend D has pressed the number or typed the number of his friend X, and that's how he has called his friend X, right? When he was pressing or when he was typing the number of this friend X in his mobile and pressing call, what happens is he is producing the waves or electromagnetic waves of frequency, which is the resonance frequency of X. Hope you have followed. When person D types the number of mobile of person X and says call, or when he presses call, signals of frequency which is exactly equal to the resonant frequency of X will be starting from mobile D. Will they go to only X? No. They will go to C, they will go to B, they will go to U, A, everywhere. But who will be receiving it? Only X will be receiving it. Nobody else will receive it, because that frequency resonance circuit is found only in X, not in C, not in B, and not in A. So suppose your friend, say friend C calls you. If your friend C wants to call you, what he should do? Friend C should type the number of your mobile and say call, presses call. When he does so, his mobile, C mobile, will produce electromagnetic waves or electromagnetic signals of frequency which is exactly equal to the resonant frequency of mobile A, your mobile. So those signals will go to mobile C, mobile D, mobile A, everywhere. But which mobile receives it? Mobile A only. Because it's resonant frequency. Other mobiles do not ring. So now come to the point here. Come to this graph. Then we will have the formula later. So come to the point, you have a circuit like this which responds to the frequency, or which gives the current like this. At the resonance frequency, current will be maximum, and if you go away from the resonant frequency, current will be decreasing, and this is Im maximum. Out of all the peak values, at resonance, highest peak value will be obtained. This is current, right? Current here. Current in y-axis, frequency in x-axis. Okay. Now, if you find that current is maximum at resonant frequency, say 10 ampere. I'll get an example. Say maximum, Im maximum is 10 amp. That means plus 10 peak value to minus 10 peak value. You get full current now. You are getting the complete current. Now, whether current is, say this is 500 hertz. Sir, you say that current at the resonance is highest. Yes. Is it exactly highest? Yes. It is maximum current. Whether current is zero at all the other frequencies? No. There is a fairly good amount of current at frequencies lesser than resonant frequency. Say you go to 490 hertz. Is it zero? No, it is lesser than 500. Sorry, it is lesser than 10. Little less than 10, maybe 9 amperes. Maybe 9.5. It is not exactly zero. What about at still lower frequency? Say 450 hertz. It is not much lower. It may be 8 amperes. It may be 7 amperes. It may be 6 amperes. Current doesn't die out all of a sudden. It gradually decreases. That means if you are not exactly at resonant frequency, on either side of the resonant frequency, current falls at a steady rate. It doesn't fall immediately. It is not an abrupt fall. And now let us select a current which is not only the highest current, some current around the maximum current. That means you just apply this to the radio circuit now. A radio circuit has a resonance circuit of this type, which shows a variation of frequency versus current like this. When you are selecting a particular radio station, you get a maximum current for that radio station, and you can hear the programs of that radio station because those signals are received by the series resonance circuit. Now if you are setting the radio frequency to a value which is less than 500 Hz, say 400 Hz, whether the current is 0? No, it is not 0, it may be some 8 amperes. That means you can hear that signals also a little bit. The current may not be maximum. You may not hear those signals as the other radio station which you have tuned. The signals are not very weak. You can hear. That means, and you see here, same 8 ampere current can be heard here also. Say it is some about 600 Hz. For 400 Hz to 600 Hz, whatever the radio stations are sending their signals within that range can be heard, because there is a fairly good current. Even though it is not 10, it is up to 8 amperes or so. That means you can't hear a particular station at a moment. You can hear multiple stations at a moment. One station will be heard, its program will be heard at the maximum current or maximum voice, maximum intensity sound, but other stations will not have so much of intensity. So this problem arises. That means this circuit must be a selective circuit, and it should be a best selector, and it should be like this, sharp like this. I think you can follow this now. I am maximum, this here is current, right, and here is frequency. At resonance frequency, the current should be highest. It should be sudden peak here. Even if you come a very little away from resonant frequency, current should fall abruptly. If you are at 500 Hz, okay, you get highest current. If you are just 490 Hz, gone, no current at all. That means it should be a best selector. And we say that this circuit is a selector of many frequencies. This circuit is a selector of only one frequency. Quality factor of this circuit is very high. Quality factor is high and quality factor is low. Okay, what do you mean by quality factor? We will define it. Of course, I have to derive the equation for quality factor actually, but for the time being I will say what is quality factor. That is enough actually for the theory exam and even for understanding. But derivation I will do it. Now, if you want to define what is the quality factor, it is the selectiveness of the circuit, selectivity of the circuit. How many frequencies it will select, whether it will select a range of frequencies, or whether it will select a particular frequency. See, this is needed for radio, isn't it? Even if you go beyond the resonant frequency, you shouldn't hear that particular station. You should hear a new station. Otherwise here, this is selecting many frequencies. And this is also needed in mobile. See, suppose the mobile circuit is like this, what will happen? Mobile will select, my mobile, if it is having a resonance circuit like this, it will select 500 Hz. It will select 400 Hz also. It will select even 300 Hz. And 400 to some 800 Hz, all the frequencies are selected. That means those who have called some other mobiles whose resonant frequency is different, those signals will also come to my mobile. Of course, they will come to all the, they will be received, they will be hitting all the mobiles. But my mobile will receive signals of other mobiles also. It will start hear me, or it will start decoding all the signals from 400 Hz to 800 Hz. That's a very bad mobile. Whatever the signals come, it starts ringing. That shouldn't be so. It should be like this. It should be highly selective. Only those signals which are sent for my mobile only, and it should be received. And signals sent from other mobiles, even if they hit my mobile, it shouldn't receive it. It should reject it. No current should pass through that resonance circuit. This is a rough idea. Actually, mobile communication is not so easy, remember. But basic idea is this one. So this should be for radio, this should be for TV communication. Why, sir? For TV communication? Because for TV communication we need to transmit signals from transmitting station to receiving station. Not a single signal, we will have to send so many signals along with the audio, video, synchronizing signal, which will say that this is the particular audio for this video, and color, brightness, everything has to be given simultaneously. So we have to see now this circuit. Sir, how do you define quality factor then? Quality factor is the sharpness of resonance. Sharpness of resonance is called quality factor. It is the sharpness of resonance. Sharpness of resonance is called quality factor. Right? How do you define it? Now we will come to this circuit. Current is maximum at resonance, right? Now you select some currents which are neither maximum nor minimum. Sir, which amount of current I will select? Let us select a current which is almost about 1 by root 2 of this current. What is the 1 by root 2 of 10, sir? 10 by root 2. That is equal to 1 by root 2 is 0.707, say 7.07 ampere. 7.07 ampere is not a bad current, right? It is a fairly good current. Okay, I'll write quality here, quality factor. Okay, and I'll call this as Im maximum by root 2. So, for what frequencies, up to what frequencies, the circuit current is, even though it is not maximum, at least maximum by root 2. Hope you are following. At resonance, I am getting 10 ampere current. Other than maximum, other than resonance frequency, we get lesser than 10 amperes. Even though it is lesser than 10 amperes, what is that current other than that maximum 10 amperes? Up to maximum by root 2. For example, how many students have been selected for particular seats, JEE or NEET this year? It is not the only first rank holder, isn't it? Students in a range are selected. Similarly, you have to select a range. This is called lower cutoff frequency, and if I call this range as delta omega, I can call this as delta omega. Above resonance frequency, there is a frequency where current drops to 1 by root 2 of the maximum value. Below resonance frequency, there is another frequency where the current drops to 1 by root 2 of the maximum value, and I call this as omega naught minus delta omega, and this is omega naught plus delta omega. Am I right? And I call this width as 2 delta omega, and this is called bandwidth. So I have some definitions here. That means this circuit, which gives maximum current at resonance, not only that, gives a fairly good current at a frequencies omega naught minus delta omega and omega naught plus delta omega. Fairly good current means how much? At least 1 by root 2 of the maximum value. Of course, here it will be say 8.5, 9, something like that. It will be more than this. So cutoff frequencies are the frequencies at which current in the circuit becomes 1 by root 2 of the maximum value. Hope you can follow this, right? You can follow this now. What is cutoff frequency here? What is cutoff frequency here? Cutoff frequency, there are two frequencies, above resonance and below resonance. Cutoff frequencies are the frequencies where current in the circuit is at least 1 by root 2 of the maximum value. And there is a upper cutoff frequency where omega is omega naught plus delta omega. There is a lower cutoff frequency where omega naught minus delta omega. And totally there is a range up to which you will get a current more than 1 by root 2 of the maximum value. Why it is 1 by root 2, sir? Actually, we are expecting power to be half of the maximum value. Wow, because suppose you draw a graph of, actually this should be a graph of power. Power is equal to I squared R, right? It is I squared R. And R is a constant, resistance is a constant. So it has nothing to do with the, it will not change the power. It depends on I squared then. Graph is same. You will get a graph like this. This is power maximum, and this is not power maximum by root 2. If power has to be half, current has to be 1 by root 2, isn't it? If I comes to I by root 2, what happens to power? Power becomes P by 2. Why? Because if you substitute I by root 2 whole square, then it becomes I squared R by 2. So select a frequency where at least power is half of maximum value, and this is omega naught plus delta omega, sorry, minus delta omega, and this is omega naught plus delta omega, and this is omega naught, and this range is 2 delta omega. What is then cutoff frequencies? Cutoff frequencies are the frequencies at which power reduces to half of the maximum value or current reduces to 1 by root 2 of the maximum value. And the range of frequencies at which current will be at least 1 by root 2 of the maximum value, or power is half of the maximum value or greater than that. So range of frequencies at which current in the circuit is more than 1 by root 2 of the maximum value, or power is more than half of the maximum value, that range of frequency is called bandwidth, or the range of frequencies between lower and upper cutoff frequencies is called bandwidth. And now quality factor is resonance frequency divided by bandwidth. This is called quality factor. So if you are asked to write what is quality factor, it is a ratio of resonance frequency to the bandwidth, and it can also be written as the inductive reactance by resistance at resonance, or capacitive reactance, or I can write it like this: inductive reactance at resonance by R, or capacitive reactance by resistance R. Both at resonance, remember, these both values at resonance, otherwise they won't be equal. So quality factor is equal to resonant frequency divided by bandwidth is equal to omega naught L by R, or 1 by omega naught RC, because omega naught C is XC, right? Or I can write 1 by omega naught CR. These are the formulas. So you may be asked to, you will have a series of definitions here. What are cutoff frequencies? Cutoff frequencies are the frequencies at which power reduces to half of the maximum value, or current reduces to 1 by root 2 of the maximum value. Then, what do you mean by bandwidth? Bandwidth is the range of frequencies where current in the circuit will be at least more than 1 by root 2 of the maximum value, or power is more than half of the maximum value. Then, what is quality factor? Quality factor is defined as the ratio of resonance frequency to bandwidth, or it is the inductive reactance at resonance to resistance ratio, or capacitive reactance at resonance to resistance ratio. So these formulas. Now you see here, quality factor is high. Why? You see here, what is quality factor? Resonant frequency divided by bandwidth 2 delta omega. Delta omega is less, automatically quality factor should be high. Here quality factor is low. Why? Quality factor is resonance frequency by bandwidth. Bandwidth is more, quality factor is less. So more quality factor, less quality factor circuit is used in TV communication, because we should have a range of frequencies. This is used in TV communication, and this is high quality factor circuits are used in radio communication. So that is what we have, and we will have still more things to come in this series resonance circuit. Of course, derivations, we have few derivations, we will do that later. These things are also important. We have covered only few definitions today, that's all. But understanding is must be more. So we will meet in the next class with lot of things in this. Thanks for watching the video. Thank you.